All right, so this lesson is on modeling with functions, and we're going to actually do a few things. We're going to pull some things together, and I'm going to show you one or two new notations in this video. So first of all, modeling, if I haven't already told you that already, modeling is just a fancy word for word problems, where we use like real world problems to apply them to the math that we're talking about. And then functions, you know, a function is something where each input has exactly one output. So we're still going to be dealing with that today, but I want to show you something new, and that is called function notation. And what function notation does is it's literally just another way of writing just a regular equation. So for instance, we've recently been solving slope-intercept equations. So slope-intercept form, or you can call this like standard notation, however you want to name it, would be something like y equals 3x minus 8. So function notation is going to literally just replace this y with what we call f of x. So function notation is going to say f of x equals 3x minus 8. And the f in this, so one thing that you need to know that this is said f of x. And what it means is f stands for function, and of x is just telling you that this is the variable that they are going to use. So for instance, if you were trying to talk about someone's height over time, you might say h of t, which stands for their height in terms of time. And you would expect your equation to look like, I don't know, something like 20 plus 1t, right, where t stands for time. So notice that the variable that you see in these parentheses is going to match the variable that you see in the equation. So let me show you a few applications of this function notation, and then we'll dive into the modeling. All right, so when we evaluate functions, it means they're going to ask us to find certain values. That's why we call it evaluating. So they've given us this function, f of x equals 3x minus 8. So I just want to show you, if this had said f of t, then the equivalent function would be 3t minus 8. If they had said they wanted us to find f of L, it would be 3L minus 8. They said f of a heart, then our answer would be 3 hearts minus 8. So notice that, like I said, this literally just tells you what the variable is going to look like in the equation. So notice that notation. So then if they ask us to find, in an example, if they ask us to evaluate f of 7, they literally want us to just replace that variable x with the value of 7. So that's 3 times 7 minus 8. Well, this is actually something that we can work out, right? I couldn't do anything with 3t minus 8 or 3 heart minus 8, but I can work this out. This is 21 minus 8, which is going to give me, positive 13. And so I would write my answer, f of 7 equals 13. And all that means is that at 7, my value is 13. All right, we could also do this with equations or expressions, rather. So they could give us one and say, find f of x plus 1. All right, and that would mean to replace x with x plus 1 minus 8. And we can work that out as well, right? This is 3x plus 3 minus 8, or 3x minus 5. So that means f of x plus 1 is 3x minus 5. So that's how function notation works. So let's look at some of those modeling problems we were talking about. So the first one is just this situation down here, all right? That's short. You can write that in your notes. I don't think you're going to die, nor will your pencil collapse from fatigue. All right, so this example, we are not going to be identifying independent and dependent variables. If you're up here reading the directions, that's something you do in science, and you don't need to really know that for this class. They are asking us to write an equation in function notation and then use it to solve. So when I do word problems, we haven't really done this yet, but when we do word problems in here, I like to do them in 3 parts. The first part is going to be to write. The second part is going to be to solve. And the third part is going to be to write a sentence or to interpret. So let's go ahead and work this problem out. It says that a lawyer's fee is $180 per hour. You should notice that rate word. How much does he charge for 5 hours? So the only thing I know about his fee is that it's $180 per hour. So my function notation is going to be f of x equals 180x, because that's how much he charges. And we still want to define that variable to say that x stands for the number of hours. Now notice in the solve category now, we are actually solving this for that given number of hours. He says for 5 hours, so that's actually asking me what is f of 5. So if I keep this function notation going, I'm doing 180 times 5, so that means f of 5 equals 900. Now, the sentence part is to interpret, well, what does this really mean? Because all of this was used to talk about a real-world situation. So for this problem, when we write our sentence, that f of 5 equals 900 literally means that for 5 hours, he is going to charge $900. And it doesn't have to be a complex sentence you write. You just want to include what the 5 stands for and what the 900 stands for, or whatever the values that you're going to get. Okay, the second example still asks us to write a function in function notation. So again, I would like for you to go ahead and copy down this word problem so you understand the context where you got your answers from for your notes. And then when we're talking about finding a reasonable domain and range. So let's start with the function itself. If I read the function itself, it just says Manuel has already sold $20 worth of tickets. He has 4 tickets left to sell, and he's going to charge $250 per ticket. So the two things that I've underlined have to do with how much money he's going to make, or what he's going to collect in sales. So I'm going to call this f of x for my writing stage. F of x equals $20 that he's already sold, plus $250 for each additional ticket. And we want to define that that means X stands for the number of tickets. Now this question is a little different because they're not asking me specifically to define how much he is going to make for a certain number of tickets. It just tells me that he has 4 tickets left to sell. So we said X stands for the number of tickets. So if we think about defining the domain, my domain are my X values, which we just said stand for the number of tickets. And I want you to think about, it doesn't make sense for this problem to be continuous or all real numbers, right? This is an example of a discrete problem. So we need to say, what is the specific domain? Well, if he has 4 tickets left to sell, he could sell 0 tickets, or he could sell 1, or 2, or 3, or 4, but he can't sell more than 4. He can't sell 3.5. He can't sell less than 0. So this is the domain that we want to use. It also says for us to find a reasonable range. So from this, we're going to go ahead and state what the range could be. So the range are our y values or our f of x values. So if you plugged in, like if I told you that he sold 0 tickets, then you would be able to tell me how much money he collected. So this is going to be his the amount collected, or the money if you want to label it that way. So we just want to think about for each domain, how much would he collect? So if he sold 0 tickets, well, we know he would have $20. If he sells 1 ticket, that's 20 plus 250 is going to be $22.50. If he sells 2 tickets, that's going to bump him up to $25. 3 tickets, right? I'm just continuing to add $250 every time. That's going to give me $27.50. And if he does 4 tickets, that's going to get him up to $30. So that is your specific domain and range, labeling for the fact that this is a discrete function. All right, so this is the last example, but I just want to show this to you about graphing. It's just kind of a wrap-up of the graphing, talking about restricted domains versus all real number domains. And restricted, we just talked about. When you restrict the domain, that's going to give you what we know as a discrete function. So we're going to be looking at separate points. All real numbers is going to give us a continuous function. So let's just take a look one more time as to the difference between those. So in this restricted domain, well, actually, I'll do the continuous first. So continuous first, we learned that there's a shortcut to graph this. I can graph the x-intercept. So if I cover up, that gives me x equals 9. and my y-intercept it gives me is going to be positive 3. And then if we very carefully connect those, we're going to get this straight line right here. Okay, this is an example of all real numbers or continuous because notice that I connected the points. The two arrows indicate that it goes on forever, right? So that's a continuous. So the same function can be graphed on a restricted domain, and the difference is, I know that it's still going to have these intercepts of 3 and 9, but the difference is they tell me the domain values I'm allowed to use are only going to be 0, 3, 6, and 9. Now notice, I've already graphed a point with x equals 0, and I've already graphed a point with x equals 9. So I've done those already. I'm just trying to find the 2 points at 3 and 6. So if I kind of continue this pattern, I can see that there should be a point there at 3, 2, and a point here at 6, 1. And since this is a discrete graph, that's all I'm going to do. I'm going to leave them as completely separate, distinct points, and I'm not going to connect them at all. Notice I'm not going to go back and try to like plot a point out here, right? Because I don't want those points. I only want the points at the domain values 0, 3, 6, and 9. So that's the difference between a restricted domain and a continuous domain when we look at just graphing, particularly when we don't see them in context.